Hello and welcome to this quick presentation on orbit plots. We are very interested in how a shaft is moving inside a fluid film bearing. The vibration can tell us about the motion of the shaft, and the motion can tell us whether there are oil or fluid instabilities, unbalance, misalignment, preload, etc., rubs, loose parts, and shaft cracks and other faults. So just by knowing how that shaft is moving can tell us a lot about the condition of the machine and any problems we may have to deal with. Now we're talking about fluid film hydrodynamic bearings. They're also called journal bearings, plain bearings, sleeve bearings, white metal bearings. But what we're looking at here is the situation where we have proximity probes or non-contact eddy current probes installed on the bearing. Now in this case we can see we've got them at sort of 0 and 90 degrees. Sometimes they're mounted in different positions, but that's not the point. The probe can tell us just what the distance is between the tip and the shaft, and then if the shaft is moving we can get that vibration change. We'll get a differing voltage signal as that shaft is moving back and forth like that, and it's that motion we are interested in. So without further ado, I'm going to bring up my orbit simulator, and here it is. So this is just supposed to simulate what's going on inside that journal bearing. So here is my shaft, and I've got my two proximity probes located in these two locations. As I mentioned, they might actually be located in different positions, but we'll just leave them there. What I'm going to do is exaggerate the size of that gap so that we can get some movement going and see what's going on. But basically, these sensors are able to detect the distance between the tip and the surface of that shaft. And if I now make that shaft vibrate, so you can see that in addition to the fact that it's just spinning, it's also moving in a circular motion there. Now, we are interested in whether it's a nice circular motion like that, or an elliptical motion, which might be a bit more common, or if due to the forces on it, due to oil instabilities and other things, if that motion is different. And if we use these two probes, we can sort of use XY coordinates to find out just where the shaft is. Now, even though we are measuring the distance between the probe and the surface of the shaft, think about it in terms of what the center of the shaft is doing. And what I'm going to do is put a little dot. Now, you might find it hard to see it. It is there. If you've got the big view behind you, behind me, you'll see it more easily. But you can see there's a green dot right in the center of that shaft. And what I'm going to do is make that green dot leave a little trail. So now you can see it's left a trail behind it. And it's showing how the center of the shaft is moving from one moment to the next. And instead of trying to visualize the center of the shaft, if we actually use these two dynamic voltage signals and plot them against each other, like X versus Y, we get an orbit plot. And there it is. That's that same circle. Now what I can do is just show you those voltage signals. So there's the voltage from my Y probe, which was up on top, voltage from my X probe, and I've also got my key phaser sort of once per revolution signal going there. So again, if I show you the shaft, there it is spinning, and this is rising and falling according to the gap there, and this one's rising and falling according to the gap there. When I plot those against each other, oops, daisy, I end up with an orbit plot. Now, in reality, the shaft might be more likely to move from side to side than it is up and down. So let's just increase the voltage on this one. So now we're getting more side-to-side movements, and if we look at that as an orbit plot, you can see it right in the middle of that shaft there, but if we see it as an orbit plot, we get this different shape. Now, all depends on what's actually wrong with the machine. You know, if I saw something more like this, that suggests that there's some preload, there's something sort of loading up on that shaft because of misalignment, and now the shaft is moving in a particular motion, and we can see the motion. It's moving, actually I've got my phase around the wrong way, but you can see it, how it's moving in that motion because there's some force. It's not allowing it to move in this axis very much. And we can go through with lots of different demonstrations. If there was unbalance, there might be a lot more motion. If there was you know, rubs or instabilities and oil whirl and all sorts of things, you get all kinds of interesting looking that's just something interesting I came up with. You know, just different sorts of shapes, just depending on the forces on the shaft. There's a lot more we could go into with this, but I hope you just get the idea of how those orbit plots work. So, as I say, there is a lot more we could talk about. We could talk about the sensor installation and the sensitivity and the conventions used, filtering the signals, whether you're looking at an orbit of just the 1x vibration, the filtered vibration or the direct vibration, all of it, dealing with shaft glitches. You know, the surface of the shaft isn't going to be perfectly flat. It's going to have maybe some surface defects, scratches or whatever, just slight. The metal may not be homogeneous, which means that the way the sensor works is going to vary. We have to deal with these things. We use key phases to get a 1x reference. We can look at forward and reverse precession and generally diagnosing fault conditions. We give that training elsewhere basically, but the point is that the motion of the shaft tells us a lot about what's happening inside the machine. Putting an accelerometer up on top of that bearing does not give us that same information. It's only one-dimensional for starters, plus the vibration inside can be heavily damped as it goes through that fluid film up into the metal of the bearing and up to the top of the accelerometer. We still sometimes use the accelerometer so we can see how the bearing is vibrating compared to how the shaft is vibrating, and with that we can tell how the shaft is vibrating relative to ground, but that's another story as well. Anyway, I hope you have a clearer idea about how orbits work, how they relate to the movement of the centre of the shaft, and how the different shapes indicate different fault conditions. Hope you found it useful.